Okay, so it's great to have Sharat here. Sharat started as an undergrad at IIT Zurich, and then he went on to do his PhD from University of Waterloo. So right now he's a postdoc at ETH, and his research interests are in approximation algorithms, particularly in optimization and uncertainty. And over to you, Sharat.
Thanks, Nikhil, for the introduction. Thank you all for having me here. Thanks, Nikhil, for taking care of the arrangements. Thanks to the department and staff for the coming here was smooth. Okay, so today I'll be talking about one of the main things that I do for research, and that is optimization under uncertainty. So
just click on the screen.
Okay. Right. So quick background on what I do. I work in combinatorial optimization. I design approximation algorithms for a living. So what is combinatorial optimization? It's the task of finding the best solution among a finite set of possibilities. A very crude picture of what we do. For instance, you could have a manager who is trying to, maybe here, yeah. There could be a manager trying to distribute tasks among workers, and the manager is trying to make sure that no one is overworking or underworking. Like it's fair. Or you could be interested in solving some sort of a network design problem where you're interested in connecting a bunch of vertices in a graph, like all the vertices in a graph, and you're given edge length, so you want to find the minimum connected subgraph of this graph. There could be a salesperson who is trying to visit all their clients in some geographical area, and they're interested in finding a sequence through the cities that they should visit so that the total length or total travel time or total cost is minimized. So that's the traveling salesman problem. Often it is computationally prohibitive to try all possibilities, so we need to exploit some structure. However, many such problems are NP hard, and P versus NP rules out polynomial time exact algorithms. So efficient algorithms are ruled out. So instead, what we do is try to look for approximation algorithms. Let's settle for near optimal solution. So what is the definition of an alpha approximation algorithm? It takes an instance of the problem and outputs a feasible solution S with the following guarantees. First of all, it runs in polynomial time in the size of the input. And then the other property it satisfies is that if it's a minimization problem, so let's say there's a notion of cost, so the cost of the solution will be within an alpha factor of the cost of the cheapest solution. Or if it's a maximization problem, then the profit of S is at least alpha times the profit of the most rewarding solution. For minimization problems, this alpha is at least 1. Maximization problems, this is at most 1. Let me now talk about a little bit about optimization under uncertainty. Uncertainty is ubiquitous in many real-world optimization problems. It's unavoidable. Like it might happen that the manager is distributing tasks without actually knowing how much time it would take. He only has crude estimates of these, and it might happen that on a typical day, one of the workers is working overtime, and they're very unhappy about it. Or it might happen that congestions might occur due to external factors at like random streets and intersections. So the network that you thought was a good connected subgraph might no longer be such a good connected subgraph. Or it might happen that like the traveling salesperson, they receive a call from some of their clients that they're canceling the appointment. So you might have to update your tour adaptively. A straightforward extension of approximation algorithms for the deterministic setting often.
No, it's fine.
Okay,
Don't-
is
don't-
the recording. Okay,
Yes.
right. Because I don't want to block the view for some of these people. Right. So usually a straightforward extension of ideas from the deterministic setting might not yield good solution. In particular, the best solution for averaged or expected data might be a very poor solution for the stochastic instance.
What I told you is stochastic instance.
What?
So what I told you is stochastic instance. Is it this uncertainty thing? That's what.
Yeah, the uncertainty. Like there is some randomness in the data, and like if you just look at the average data, then that might be a bad solution. So I'll give like more concrete examples. It's just a good slide. Let me quickly talk about the outline of this talk. I'll talk about two research topics. They're closely connected to each other. The first one is on stochastic optimization with norm objectives. And the second one is on stochastic load balancing with machine reservations. The third part, I'll just like talk quickly about my plans for teaching and supervision. There is also a fourth part that I haven't mentioned here, some of the other projects that I worked on. If we manage to get through the proofs quickly, then maybe I'll comment a bit more on that. So let's get started with the first one. So this is joint work with my PhD advisor, Chaitanya Swami from the University of Waterloo. And yeah, so what is this work on? So we introduced a very general model of single state stochastic optimization, which we call stochastic minimum norm optimization. So the setup here is that you're trying to solve some minimum minimization problem subject to a solution being feasible. So the abstract setting is the following. You have some combinatorial optimization problem where the costs involved are random variables with some given distributions. Assume that you know these distributions, like you have full information. You have some set of feasible solution sites. And each solution, each feasible solution induces a multidimensional cost vector, y is, such that the coordinates of y are independent random variables. They don't have to be identical. They only have to be independent. Each coordinate can have its own distribution. And so I refer to them as product distributions. It's convenient to talk about it now. And I'm also given a monotone symmetric norm F, which maps m-dimensional vectors to a non-negative real. And this norm is monotone and symmetric. Monotone means increasing a coordinate that does not decrease the norm. Symmetric means it is invariant under permutations of coordinates. And I'll only assume that we have value oracle access to this norm. Okay, so what is the optimization goal? Find a solution S. It induces some random vector y. Aggregate all the coordinates into one entry using the norm, and then look at the expected value of the norm. And let me remark here that the sum of entries and the maximum entry, these are monotone symmetric norms. So it is not just like an abstract problem, it contains like popular objectives that we care about. And let me also remark that you fix a solution. You don't adapt yourself to the stochasticity. You fix one solution and you look at the quality through an expectation of the norm. Let me state now a concrete problem. Stochastic minimum
If you know
norm.
a solution,
Okay.
if you know a solution, why is it still a vector? You still have to compute a cost, right? So it's spanning tree and just add the
Yeah, but the norm might not just add, it might do the L2 norm.
No, but so if S is a spanning tree, what is the vector y?
Yeah, I'll get to it. It's each of the edges go on one coordinate each.
Okay.
Yeah. So let's consider this concrete example. It will be clear.
Once again, so what is the expectation over the coordinates? Or
Oh no, the
is
expectation
randomness-
you are all the randomness in the cost variables.
Okay.
Okay. I think this example will make it some of these. Also, please interrupt me if there are any questions because the model might be a bit confusing at times.
So M is the number of random variables.
M is the dimension of
Yeah,
the
that
cost
is
vector.
the cost vector.
Okay, so let's start with a graph, undirected graph on n vertices. Edges have stochastic weights, and the edge variables are independent. Feasible solutions are spanning trees. each spanning tree induces an n-1 dimensional cost vector. For this spanning tree highlighted in red, you take the edge weights and put it on each a separate coordinate. You're given a monotone symmetric norm that is n-1 dimensional. You're interested in a spanning tree that minimizes the expected norm of the induced cost vector. So there can be like a lot more variables, but for spanning trees, there will be some n-1 variables that we care about. You aggregate them, you might add up the lengths like you do usually for spanning trees, or you could look at the maximum, which gives the bottleneck version, or you can look at some other norm as well.
So good question. So what's the norm here? Is the function the norm?
Yes, f is the norm. And you have a black box for this. You can just ask, this is my m-dimensional vector, like with some fixed real entries, and it will spit out.
My point is that if you have y, there is an arbitrary cost, and you have an f, why do you need to apply it? Just compute the cost as f of y. Why do you need both of these variables?
Because they independent.
So in this case,
What is it?
So firstly,
the stress.
so the thing is that S here in this example, for instance, S refers to a specific spanning tree.
Okay.
Yes.
But the cost vector is a function of what the stochastic weights on each of the edges also were.
Yes.
Okay.
Yeah, the edge weights go into this entry.
Yeah.
And each spanning tree gives a different vector. And you look at the norm. The norm is also a random variable. And you aggregate all of that together into one number by looking at the expectation.
Why can't I call y to be the norm? Why do you need f to be the norm and y to be the edges? Just call y to be the sum.
Oh, sure. That's a matter of representation. You could, yes, all of these are like connected, but I think it's, yeah, you could look at f of y and then call that as like the cost.
Yeah.
But then you lose information. This value is coming from doing some operation. This is the.
But your cost is okay. Sure,
Yeah.
that's fine.
Yeah, the underlying cost variables are these. These are the ones that are like, that is like how you aggregate is depends on the norm. That's the idea. Let me give another example. So this is stochastic minimum norm load balancing. Here you have a set of n independent stochastic jobs and m identical machines. And the job processing times are random variables. An assignment of jobs to machines, you put each job on one machine, induces a load vector on the machines.
If you put, so is there some further structure that you want? So there is actually a very large collection of these YIs, and every solution will actually choose a set. I think is that what will always happen? Or?
Yes, something like that. Like, yeah, you basically have.
Otherwise it looks too generic, because then I don't even know which Ys I will see.
I think that will be the challenge.
Makes sense, right? I mean, like you only know some distribution for each edge, right?
No, that is fine. That's what I was saying. So basically,
Y is not even the random variable. Y is some function of the random variable.
Yes, that's correct. That's
So
correct.
now you're applying a function to a function, which is
No, but the assumption is that every coordinate of Y is an independent random.
But if
yes,
you
but then
get
which
one
coordinate
coordinate
also
function,
depends upon the solution you choose.
Yes.
Like
Yes.
Yeah. So that's what. So like there's an implicit assumption that there's actually a very large collection of independent random variables, and each smallest chooses a subset of the same size.
Correct.
I think that's more special.
In the load balancing setting, there will be something different, slightly different.
Okay.
There is a little bit of aggregation happening.
But
yeah.
But okay, so there's one more aggregation happening. But
Exactly.
still there is this large collection of independent variables that.
Yes. The source is always like.
Yeah.
Yeah.
That is mixed advanced. It is independent of this S.
Exactly. That is the data you get.
Yeah.
Whereas the solution that you pick, these solutions are themselves.
Will pick some small fraction of it, then do some aggregation.
Yes, exactly. And often these the aggregations that happen, there's some algorithmic complexity involved in finding those solutions already in the deterministic case. Yeah.
Okay.
Right. So in the load balancing
More confused. So I was under the impression that the following is happening, which is that the underlying problem statement has a whole bunch of random variables.
Yes.
Once you choose a certain solution, there is a certain, cost vector that comes in. The only assumption of the cost vector is that each coordinate of the cost vector might depend on some subset of the random
That
variable.
is true. That's
But that doesn't have to be an aggregate in the sense of.
no, but I think in every
Correct.
aggregate you have to be aggregate because this is similar to this lower local lemma type thing that you usually do in the cross setup. That like there are events, but these events are not really arbitrary events. They are like clauses of some underlying independent sets of
Yeah.
random variables.
But
But they are like specific, like just functions of those. That's how you do it.
oh, that's okay.
Yeah,
Sure. Okay.
Yeah. But as long as we only
the function of some
Okay, understood.
disjoint subsets.
So
Right,
that's
yes,
so the fact that
correct,
the job can only go on one server.
Yeah.
exactly,
Yeah.
exactly. If it were going on multiple, there would be correlations.
Yes.
Right? That's right. So jobs 2 and 3 go on machine 1, the load on machine 1 is P2 plus P3. And you do this for each load, each machine load. And the objective is to find an assignment that minimizes the expected norm of the load vector. Okay, so I hope the setup is clear. And you can ask such questions for many different combinatorial optimizations.
So the two invariants are that each coordinate is independent and that each coordinate depends on the small set.
The small set is not that.
But it disjoints us.
Yeah, disjoints.
But then why can't I just have one coordinate that is f of that?
Then you have lost information. Like, how do you even know like what f of y will be?
I don't, that is the value I have. F of I is z. I just compute the expectation of z.
Yes, yeah, but you have lost a lot of information now. You don't know what z is now. Like, if you just write it as z, you have lost information that.
I also don't know what y is.
No, but if I know I have two y and y primes, the z and z primes will be f of y and f of y prime. But if you just gave me z and z prime, how do I know which y and y prime they came from? Like, there is something like there's more information encoded in like saying that it is always f of
So this
some.
because F is very structured, right? It's supposed to be.
So we know f in advance.
Yes,
Yeah,
like there is a value oracle, like there's a promise that it's a monotone symmetric.
I'm not sure about that.
Right. So, yeah. So, what is the significance of this model? Why are we studying something at this level of generality? So, the idea is that we want to have a principled approach for designing algorithms for many different class of combinatorial optimization problems and many different norms. Otherwise, usually in literature, you see different algorithmic techniques for the sum norm, for the max norm, LP norms, and so on. Like, can we do all of those together in one shot? That's the idea. And that's the goal. So working at the generality of monotone symmetric norms has several benefits. First of all, like it contains popular objectives that people care about, such as the sum of cost and the maximum cost, which model utilitarian and egalitarian objectives. It also contains LP norms and top K norms. These top K norms are, in some sense, combinatorial version of what LP norms do. They interpolate between L1 and L infinity norms. And top K is the sum of K largest entries in a vector. And another benefit of working with monotone symmetric norms is their closure properties with respect to taking non-negative linear combinations. Alpha 1 times F1 plus alpha 2 times F2 is a monotone symmetric norm given the promise that F1 and F2 are monotone symmetric norms. And we have another closure property with respect to pointwise maximums. This is a very interesting closure property. It gives you a lot of power. So let's say you had a feasibility problem with multiple norm budget constraints. You want to find a solution such that the rth norm fits within some budget BR. You were interested in finding such a solution. You can actually cast it as a single norm minimization problem. Just consider the monotone symmetric norm G, which is just the pointwise maximum of the scaled versions of these budget constraints. And then you just model it as a minimization problem. If this optimal solution is at most 1, then you know that this problem is feasible. So now I want to talk about like the tools that we developed for stochastic minimum norm optimization, but it first makes sense to look at what we know for the deterministic portion of the problem. So here is some definition of majorization. This will be important to us. A vector x majorizes a vector y if the top k norm of x is at least the top k norm of y for all k. So what this means is that like sort the vectors, the prefix sums of x dominate the prefix sums of y. A very classical result of Hardy, Littlewood, and Polya, almost a century old, from majorization theory is that if x majorizes y, then f of x is at least f of y for all monotone symmetric norms. What this means is, like, in some sense, think of the top k norms as the basis for controlling all monotone symmetric norms. Just focus on these m norms, then you have control on all monotone symmetric norms. Chakrabarty and Swami's framework for the deterministic minimum norm optimization problem is based on this idea. Like,
So isn't that more general? That is every monotone convex function, monotone symmetric convex function.
yes, it also holds for more general thing. I think you also have to put some restriction on the sums being equal, and then I think you can
Yes,
extend it
sums
to
being equal.
right. Yes, yeah, it does hold for more general settings as well. Right. So the first question is, why can't we simply look at the expected cost and use Chakrabarty and Swami's framework? Yeah. So the problem is, usually the expected norm of a random vector and the norm of the expected vector, they can differ by a huge factor. So this can lead to poor optimization decisions. So if your lower bound is weak, it can actually throw you off in the wrong direction, send you off in the wrong direction. So let me give a concrete example. Imagine a random vector which has Bernoulli 1 over m in each of the coordinates. So each coordinate is 1 with probability 1 over m and 0 otherwise. What is the expected maximum? Roughly 1 minus 1 over e. With that probability, one of the coordinates will be at least 1. And then what is the maximum of expectations? Just 1 over m. So that's a huge factor in gap. So natural question to ask is there a stochastic version of majorization inequality? Okay. So what is our core technical result? To state this, I need some notation. So for any deterministic vector, as in like an m-dimensional fixed vector, I use the notation x with superscript of downwards arrow to denote the vector sorted in decreasing order. So here's the main result. For any monotone symmetric norm f and for any product distribution y, you are interested in the expected norm of y. The result is that it is within constant factors of the f applied to the expected sorted vector. Okay. So, but before I talk more about this, let me, like, on the previous slide, we saw that if you exchanged expectation and f, you lose a lot. So you lose something proportional to the dimension. Instead, if you sort it first, you don't change anything yet because it's a symmetric norm. Then you apply instance inequality. So you only apply instance half of the way, not like fully. You only get a constant factor loss. And what is this expected sorted vector? It's simply the order statistics of a random vector. In the kth coordinate, you have the expected kth maximum in this random vector. So let's recall our original goal. We want to find a solution so that the expected norm of the cost vector was minimized. Using this theorem, we might as well just focus up to constant factors. We'll focus on just minimizing the norm of the expected sorted vector.
I want to understand what this sorting is doing. Is it throwing out the randomness in some sort? Like what?
Once you look at the expectation, yes, it takes it, like, yeah. So what's happening is here you're applying expectation or norm on different like choices of y, different samples of y. Right? What it is saying is it doesn't matter. You don't have to do so many non-calculate. Like what matters is what is the first maximum, second maximum, and so on. Like just look at the aggregate, like the expected values, and just look at the norm of that order statistic, and that is a good estimate.
I see.
In some sense, like here you only do a single norm calculation in some sense. The essence of this randomness is in the order statistics. That's what it is saying. Right. So on the previous slide, I had asked whether there's a stochastic version of the majorization inequality. Here it is. So suppose you have two product distributions x and y. The expected top k norm of y is bounded by the expected top k norm of x, and this holds for all k. Then the expected f norm of y is within constant factors of the expected f norm of x for all monotones. So this result is the approximate stochastic majorization, not quite exact stochastic majorization. That should not be possible. There are like lower bound examples showing that there is a gap between these quantities.
So can you say
Question here.
Yeah, one moment. So, yeah, there's a question online. Let me just take this.
So Rahul, can you go ahead?
Yeah. So when f is the max of all the elements,
Right.
can you not do better than 8? It seems it's a rehash of. So the,
There is no loss for top k norms or non-negative linear combination. So basically, any norm which is just ordered, this statement is not saying anything. It's just a trivial equality. The
yeah, it
state
seems to be a restatement of some sort.
That's correct, because the sorting doesn't change. But if you have a statement for L2 norms,
Right. Okay.
yeah,
Got it. Thank you.
yeah, good question. So this theorem is only applicable when your f is such that it has at least two different ordered norms. Otherwise, it's just an equality. Right? You had a question.
asking that is 8 tight for something?
No, I believe that it should be at most 2 or something, that it's not very lossy. We can show up to 7.6 something. Yeah, and the lower bound example we have is like 1.21. Maybe it can be pushed to 1.28 something. But yeah, 8 it doesn't seem.
What happens in the Bernoulli setting? I'm just trying to understand
Right.
the previous example in this theorem. So if all the coordinates of y were basically Bernoulli,
Right.
what would the sorted versions look like?
Right. Yeah. So the first entry will be 1 minus 1 over e, the expected maximum.
Oh, I see.
Right. And the second maximum will be something maybe like 1 over.
So that's what you would get.
Yeah, there are
that
these
was
values.
within a constant factor of.
Exactly. If you applied any norm to that order statistic, will stay within constant factors. Okay. Good. So approximate stochastic majorization suggests a very natural strategy. The first component, so this is part of our approximation algorithms framework. The first component is to work with simpler norms. So let's start with the goal of obtaining an alpha approximation algorithm for our abstract problem. This one reduces to this following multi-budgeted problem. I wanted to find a solution y. I wanted to find a solution for which expected f of y was within alpha times expected f of x, where x is the optimal cost vector. This is up to constant factors equivalent to finding a feasible cost vector y such that the expected top k norms of y are within order alpha of the expected top k norms of x. And you don't have to do it for all k. You can sparsify the case and you only do it for powers of 2. This can be done because the top 2k norm is within a factor 2 of the top k norm.
Can you go back to the
Yeah.
No, this is theorem regulation. Okay. Is there something, suppose in the toddler, suppose I know that the expectation of top k of y is less than equal to, let's say, I add another factor, then the same result will
Of factor 5?
Yeah.
Norms are homogeneous. So the same factor will just carry over. Right. Yeah. So, okay. So the first component is first working with simpler norms. But this is more like a multi-budgeted optimization problem now. The second component is to work on a stochastic optimization problem with a single top k norm. If you want to understand the multi-budgeted problem, you have to understand the single budget problem. And that is a single top k. And we give some tools for this. And this is already like a challenging setting because top k norms are non-separable. Like LP norms, you know what is the contribution of each coordinate at least, like how it appears. Top k norm depends a lot on like which other coordinates, what are they doing, what their values are. So what are our approximation guarantees? So we use our framework to obtain constant factor approximation algorithms for the following settings with arbitrary monotone symmetric norms and arbitrary stochastic weights on edges. I won't describe like the precise model. We can obtain constant factor approximations for spanning trees, matroid bases, traveling salesperson problem, and boundary degree spanning trees. We also obtain approximation algorithms for stochastic load balancing with the arbitrary norms. First of all, if each of the jobs are weighted Bernoulli jobs, so either they take size 0 or some positive size, then we obtain a constant factor approximation. Observe that it's like the simplest stochastic setting in some sense, like either take size 0 or some positive size. And this result strictly generalizes Chakrabarty and Swami's result on deterministic minimum load balance. For the general case, we give a log m over log m approximation. Here, like jobs can be arbitrary distributions. Jobs can have arbitrary distributions. And for the very special setting where each of the jobs have Poisson sizes, they're Poisson random variables, we can obtain a polynomial time approximation scheme, a 1 plus epsilon approximation for any epsilon greater than 0. And of course, the runtime will depend. We'll have like n to the 1 minus 1 over epsilon dependence in the runtime. Our techniques also work when machines are unrelated. That is, the processing time of a job may depend on the machine it goes on. And we also give a constant factor approximation with arbitrary job sizes, but the norm has to be a top k norm. So the open question is this one. And also I'll remark here that this is a substantial generalization of the result of Kleinberg, Rabbani, and Tardosh on identical machines for the infinity norm case, and Gupta, Kumar, Nagarajan, and Shen's result for unrelated machines case, again for the infinity norm, the max load. Okay, right. Oh, and also another remark would be this one. This p-dash, this is also substantial generalization of Day, Khanna, Lee, and Nick-based result for the infinity norm. So they considered the max load setting with Poisson jobs, and they gave a p-dash. We show that it can be done for all norms. Yeah, let me maybe quickly go through why does this co-result hold. So why is the expected norm of a random vector within constant factor of the norm of the order statistic? So the lower bound is easy. If you sort y, you still don't lose anything. Then you apply Jensen's. Norms are convex, so the lower bound goes through. For upper bound, we use deterministic majorization, as in majorization, the classical result, and concentration inequalities. Okay. So let me define this function beta of y. So given any vector y, I'll define beta y to be the smallest scaling factor such that the scaling factor times the order statistic majorizes this vector y. What that means is the top k norm of y is bounded by b times the top k norm, the expected kth maximum. The top k norm of the expected sorted vector, which is the sum of the expected lth maximum for all L going from 1 to k. So by deterministic majorization, f of y is within beta y times the f norm of the order statistic. So that's just by definition and majorization. So the expected f norm of this random vector y is expected, what is the beta value of this random vector y times just this lower bound that we have. So the only thing that's left to show is that the expectation of this beta function is at most a constant. So why does this beta function concentrate so well within a constant, like an absolute constant? That's the question. So let's again look at the order statistic, and let's also look at this curve. What is this curve doing? It's a plot of the expected number of coordinates in y that exceed a certain threshold t. I have t here. And observe that the expected number of large coordinates is simply the sum of the probabilities that a particular coordinate exceeds t. So it's just the upper cumulative distribution function stacked up. Now, for any k, because of the definition of the expected kth maximum, it cannot happen that too many coordinates of this random vector are larger than this. You will get a violation of like Markov's inequality or something, or like just the averages won't work out. So on an average, you don't see too many large coordinates. That's what it is saying. So by Chernoff bounds, you can argue that you don't see more than b times k coordinates that exceed the expected kth maximum. And the decay is, so you have some expected kth maximum, it is some quantity here, like the expected maximum, expected second maximum, third, and so on. And for each one of them, you know, like the expected number of coordinates is within like the respective k. So if you go b times k, then you get a decay. And that looks like inverse exponential in b and k. This is nice, this term, because you can apply a union bound over all k. And you only like still have an inverse exponential in b. And so you do a simple integral calculation and you get a constant. That's the high level idea. Right. What are some open questions in this line of work? First of all, the most pressing is there a constant factor approximation for stochastic minimum norm load balancing? With arbitrary norms and arbitrary job size distributions. Like if you specialize the norms to top k norms, we know what to do. If you specialize the jobs to Poisson or Bernoulli's, we know what to do. Our current guarantee, best guarantee is log m over log n. Another question is, this is probably a very nice question for like undergrad students to work on, like for a project, like how best can you bound the expected norm of the order statistic. It's a nice short-term goal to improve this. And what about other settings of stochastic mean norm optimization? Our core result tells you that you only need to look at norm of the order statistic, but there is still an underlying optimization problem to solve. So we still haven't been able to extend it to bipartite perfect matchings and k-clustering. So these are some nice settings to consider for like more long-term projects.
Sharat, question?
Yes, please. Yeah.
Yes, I mean, do these results generalize in the learning setting when you don't know the distributions? You have sequential, let's say you are just given sample access, it's a sequential game. And this Y's are coming from the same IID distributions, but you simply don't know the distribution.
Yeah, I guess maybe using the samples I can
You
infer.
probably need concentration for the max norms, right? Max k norms, top k norms.
Right, exactly. Because I think if it is IID, then you already know that there is only one order statistic that comes out. It's always, is that what's happening? Like when you say everything is identical?
Yes. Let's say, I mean, in the simplest setting, because you can also consider the same problem in the adversarial setting when these are not coming from in a distribution. But in the simpler setting, let's say it's IID. Can we just estimate this top k norms?
I think, yeah, it should be possible. You just
Take a running estimate of that and then apply this algorithm. I mean, just
yeah. I think it should be possible as long as you get a good estimate for the top one norm, the expected top one, Like if it's an extremely rare event, then of course you need to adjust your number of sampling steps accordingly. But once you have a reasonable estimate for the expected maximum, the other ones can be crudely estimated up to relative and additive guarantees. That should work out. Yeah.
Okay. Okay. Thanks.
If there are any pressing questions, I can take them now, or I can also take them towards the end of the talk. The second part is on stochastic load balancing with machine reservations. This is joint work with David Alleman, who's Swami's current PhD student, Naveen Garg from IIT Delhi, and Neil Olver, who was my postdoc host when I was at the London School of Economics. This work is not yet published, so just letting you. Okay, so until now, what we have seen is we took a decision and we didn't do anything. We paid for the stochasticity by looking at the norm and then the expectation and all of that. What if we wanted to also change our solution a little bit based on the stochasticity? It's a natural question to ask. So let me talk about something called reservations in load balancing. I'll give a motivational example for this. I have a law firm which has M attorneys and N clients. The clients have retainer agreements with the law firm. What this means is they pay them regular premiums so that they get priority legal advice. They don't want to wait the law firm to catch up with their case or something. They want the lawyers to just quickly respond to their queries. And suppose the firm says, okay, I'm going to distribute the clients among the attorneys. Every attorney gets 2 clients. And the assigned attorney is familiar with their client's needs. Now, what if a lot of clients assigned to the same attorney simultaneously need advice? So both of Mike's clients call them and they're like, okay, and some very urgent legal matter, please advise us. Right? Then he'll have to let one of the clients down on that particular day, which is unfortunate because the clients would be dissatisfied with the turnaround time. They are paying big money for this legal advice. The firm could instead solve this problem by reserving more than one attorney for each client. And now each reserved attorney must know the context for that client's case. And the idea here is that an overloaded attorney could offload some of the cases to the other reserved attorneys. So the question is, what's the trade-off between the turnaround time and the number of reserved attorneys per client? That's the question we're interested in. In the first part of the talk, we always gave each client to one attorney. But now it's like there's a little bit of wiggle room. Let's start with a toy example.
What is the model? Do they need advice in a Poisson process? Or?
It can be a general distribution. I'll fix the exact problem definition soon. Let me start with a toy example and talk about some 2 extreme levels of reservation. Toy example has M attorneys, M squared clients, each with an IID Bernoulli 1/m demand. So on each day, a client might call you and ask for like a day's worth of effort, legal advice that takes a day's worth of effort, or they don't call you at all. That's the model. On an average, you expect M clients to call you on a random day, and you have M attorneys. And your goal is to minimize the expected maximum turnaround time. Who is the most overloaded attorney on a typical day?
Okay.
So let's reserve every attorney for each client. Let's say it's very unreasonable, but let's play along. If our clients need advice, then the max turnaround time is ceiling of R over M. And you can argue that the expected maximum turnaround time is a constant. It's the best possible guarantee because every attorney is available for every client. So that is great. But it is very wasteful and impractical because every attorney has to be aware of every client's context or needs. Let's look at the other extreme. What if I reserve only one attorney per client? It makes sense to assign M clients to each attorney. So on an average, you expect one client to call. But we all know what happens using the balls and bins analysis. Right? If each each entry is a binomial random variable with mean 1 or a Poisson variable with mean 1, and you have n such entries, then the maximum load that you see will be like log m or log m. So this is quite bad. So it's efficient in terms of context. Only one attorney needs to know the context for a case, for a client, but it is very poor in terms of turnaround time. And also observe that the turnaround time blows up when an attorney falls sick or takes leave or leaves the firm. And in some sense, even though that is not a concern in today's talk, but you expect in practice that people will be having more attorneys per case. So the question is, how powerful is this reservations model? So let me first state the setup clear.
Again, I just want to understand. So in the can you quote that? So what is this model in this reserve one attorney per client thing? So
each client goes to a fixed attorney, one.
But where is the binomial coming?
Because you have n clients per attorney. So the load on that.
But then I mean this you can get around by two choices, for example, right, to make it much smaller.
Correct.
So but then what does that work? So it's basically like instead of doing just a random decision, you choose two and then go to the lower.
What do you think the answer would be in that case?
No, I know what the answer is, but does that make sense in this case?
Yes, it does make sense. So, but let me.
Yeah, but then so then
in this extreme case, it is log m over log m.
Yeah, it goes to log m. But
right.
So then so that helps, right?
Yeah.
So that's another benchmark, or
doing two helps.
But it's not like we're assigning two attorneys in that model. We're assigning only one still. It's just that
at the end of the day, on any given day, only one attorney will handle the case.
Yes. So I'm just trying to figure out if that is also a valid benchmark for this or not.
Like the lower bound that you get from
the upper
bound.
Yeah, the log m that you get.
Right. Sure. You could also compare against that. That is.
Maybe it does not mix. I mean, I just want to make sure. So because
this model is more like if you were to reserve k attorneys, what is your cost going to look like? That is the question. If you reserve one attorney, then this is the answer. If you reserve,
if you reserve, you can get one reservation with a much lower cost, right? By just two choices. If all what we are saying works, right? So each time you choose two of the attorneys.
That's two reservations.
That will be reserved.
You give them to the lower one. That's the point.
It doesn't matter. That's why there are two people who are accepted.
The question is how much effort does an attorney need to do to prepare for the clients? Okay, there are two guys.
Yeah, so that's also I'm not understanding. So is it? So it's not making sense. So then then I don't understand how this assignment is happening.
Let me explain the setup. It will be a bit more clear. Like I'll state the problem statement, and it will be a bit more clear. So you have given some identical machines, and you have given a set of stochastic jobs. The jobs have some stochastic processing times.
Okay.
We are given a reservation parameter k. It's an integer. In the first planning stage, using only these job size distributions, you reserve up to k machines per job. Okay, so I'll call sigma k reservation when it chooses up to k machines per job. The examples we saw there was one was an M reservation and the other extreme was a 1 reservation, which is an assignment. In the second stage, the job sizes are revealed to us. This is like the day-to-day thing when the clients have already called, the manager knows, like the law firm knows how many requests have showed up. That's the idea here. We can choose any assignment pi that is consistent with sigma, the reservation. For each job, you can put it on a reserved machine. That's a consistent assignment. For instance, for each job, you chose like some k attorneys, here 2 in this case. And you have some two reservation in this figure. And you might say in the stage 2, when some realizations come, you might say, okay, this for today, this legal advice will be given by this reserved attorney.
So in the previous one, when you said 1, actually the sigma was just a function, right? Because I said, no matter what size is revealed, I will do it to that.
Yeah, exactly.
It was choices also. So you just
two choices will be again you have to reserve one more attorney.
No, you just so at stage 1 before the sizes are revealed, instead of sampling randomly, you sample 2 of the machines.
Yes.
Choose the one which has a lower load right now.
But there's no load right now. You don't
Yeah, there is no load.
No, load as in you just count, right? How many, like, so
jobs
there
are
are
after the assignment. What? You have a set of clients. You have to
there are
assign
jobs,
them.
right? So you just
Yeah, there are jobs, but you don't know
you
the
just make sure each attorney does not get a certain, like, the total number of jobs that get assigned to any one attorney in stage one is log n.
But all jobs
Oh,
are
no,
not
no,
even
no. All
related.
jobs might have different sizes.
Yes, so there are log n by log n thing because that assume that the size is the same.
Piyush, can I suggest let him
Yeah.
put the full formal problem and then we can discuss this? I
Okay.
think there are certain things which are missing and I think he'll fill in.
Okay.
I think most of the questions will be answered there.
Yeah. So you don't, when you're only given this random distributions, you don't quite know the sizes that will be instantiated. It's on the day of, imagine like,
No, I
yeah.
understand, but then I don't know the log n by log n calculation. So yeah, well, let's give
right,
because that also assumes the size are the same, right? That
or more like
that
0 or 1.
Yeah, so like again, so when it's 0 or 1, the log n thing also works, right? So what I'm saying is that in any situation, I cannot imagine a situation where the log n by log m works and the log n does not work.
I think that is true. I think
But then I think
Yeah, with two reservations, yes.
no, it's not two reservations, it's one reservation.
no, it's
That's no, it is two reservations.
It
So
is.
the point is, if you want the ability to say, I want to give this job to either this attorney or that
No,
attorney.
it's not that. So there's two things, right? So you can
No, what is your stage one assignment with one reservation?
yeah. So I pick two of them at random and give it to the lower one.
There is no lower.
There is no lower yet.
It is empty.
No,
There is no lower.
keep assigning it one by one. Like
You can't see the realization. It's a repetitive game. Every day the game keeps getting played.
so there I understand how the log n by log m came because that is in this
Right. Yeah. Let me explain the cost
Okay.
model and then it will be clear. Yes. Yeah. So the cost of a K reservation is you look at all realizations of the job sizes. You see what is the best possible consistent assignment with respect to the max flow, the make span objective. That's the cost of a K reservation. Yeah. So in the previous case, it was like the 0, 1 variables, and then because you had fixed each job on one machine, the max load with constant probability was log n over log m. So the expected cost is also that. So that's what was happening. And opt K is the best cost of the best reservation.
Yes,
So the cost calculation of
Okay, I'm sorry, I want to get this right. So the way this happened was that you took the job, randomly put it in one, so the balls are the jobs, right? And you put that in the bin, which is the machine.
Yes.
For now, it has just, this is stage one. Right now, that's
Sure,
the thing I told
sure.
you. And the sizes are going to be revealed 0 or 1.
Later.
Like
Later,
right? Yeah, later.
Yeah,
when you're putting
and
it.
then this log n by log m is just coming from the fact that any of these bins cannot contain more than that number of balls, and one of them will contain this number. That's the argument, right?
If you do a random thing like this,
That's the argument.
it will work for log n.
So the same thing I could have done with two choices also, in the sense that I could have, when I was doing this assignment in the beginning in stage one, I could have chosen 2 at random. Whenever I get a ball, and whichever has small number of balls, put the ball there. And now the maximum number of balls will be about log n.
No, it's not the number of balls, it's the total sum of the sizes of the balls that matters. Whatever.
Yes, but the sizes are going to be the number because it's 0, 1, right?
No, in that example.
Yeah, in that example. So I just want to that example.
Yes,
in that example, it is log n.
Yes.
And so the same cost will now be log m rather than log m by log m. Is that correct? Yeah, okay.
Yes.
So
So we should go to it after the.
in power of two choices, your base graph is a complete graph.
Yes.
But
that's
the
part.
Here also he is sampling 2 random.
But here you have to choose a base graph which is sparse.
But what is the graph?
Here, so basically with one assignment, the base graph is just a union of stars. This log.
No, I'm not looking at graphs at all. I'm just.
But there is a bipartite graph that you have to choose.
No, here it's like just a ball is going in the bin or not. That's it, right?
No, stage one is like you're choosing a graph, right? In stage one. So look at what is happening.
Like a graph,
You have
hypergraph.
to say what are the potential places where.
No, but just one in the example. Okay, because I think it's in the example it was much simpler. It is a graph, but it's like a graph in a very weird sense.
It's just a star.
Yeah, it's a single degree thing. It's for every job goes to exactly one place. It's exactly balls and bins. I think it's easier.
Yes, balls and bins. But with power of two choices, like the graph is a complete bipartite.
No, there's no graph. I still it's balls and pins. There are balls and pins. That's it. Each ball is in exactly one pin.
I think there's one thing that you're missing. That there are actually m square balls. and all of them are not real balls. So only among them are like actual balls. They're not fake balls. They're not balls at all. And you don't know.
Yeah, it's like an orienteering problem.
Yeah,
Yeah, M squared of these, and some activate and then you're.
It's not even then.
So 1 by m of them will be real.
Balls into bins. So not M, not M.
In M square. Yeah.
Okay, so then the log M by log M because that also.
So you throw M squared balls
Yeah.
into bins.
Okay,
And
so
then
then-
you are shown randomly which one of them are real ones.
Yeah.
Oh, okay. So then it's M square, not M.
The identities are not told of which ones actually came up to size 1.
Okay.
Yeah. But the thought experiment is still the same. It's like throwing in, like,
Oh.
yeah, there are very close connections. Okay. So this is the cost model.
Sir, I have a simple question on the sigma itself. So why can't it be that I'll keep for each job all machines in my assignment, because there doesn't seem to be any cost related to the size of sigma.
Correct. Like it is like it is not defined in this cost function, but we know that reserving all machines for all jobs is not very practical in some settings.
No, that I understand, but unless that cost comes into this question, which is the formal problem defined at the bottom,
Right.
isn't it always optimal to keep sigma as large as possible?
Oh, sure, but what if I restrict you to only work with k at most 2 or 3? Like I can always ask the question for what is the best 2 reservation, right?
Yeah, so even for k, let's say k is equal to 2, what information do I have at stage 1 among the different so the job sizes do not seem to depend on the machines, right? They're identical.
Correct. Yeah.
So I could just pick any 2 and that would be fine for me.
Yep, you can do something like that, yes. But not in like you can't just say I'll put like a bunch of jobs on a match. Like imagine you have created a matching on the machines and you put like m over 2 over m fraction of the jobs on a pair of machines and then 2 over m. Like you want ideally them to be spread around for the cost to be small.
Yeah, so that decision will only depend on the PJs. So the index J, that's where it will matter that if 2 are lightweight jobs, maybe they can go together, while a heavyweight job could be essentially given to a single person at a time. Is that right?
Correct intuition for more general machine setups. But maybe technical machines we can say something much nicer.
Okay, thanks.
Okay, so the price of K reservation is the worst case gap between the optimal cost of a K reservation divided by optimal cost of an M reservation over all instances. So that's the price you pay for reserving fewer machines. So what is our power of 2 choices result for identical machines? For each job, reserve 2 random machines. Then your expected cost over this random 2 reservation is within a constant factor, not log m, constant factor of the cost of an M reservation. So I hope that answers your question, like that even though M reservations are very powerful in this cost model, we are saying you can get that same power up to constant factors with just a 2 reservation.
So what was M reservation?
Like reserving every machine for every job. Here we are saying only 2 machines need to know the context for a job. And
What
that's
is it again? Still Bernoulli, MLS,
no, any arbitrary distributions. It's just you throw each job, you don't even look at the job size distribution, simply because these are identical machines. Just throw it on 2 random machines. The load will amortize itself automatically.
And I'm guessing that the reason why I don't get log m because they're m square and not m. That's why I don't get log m.
No, it has nothing to do with the number of jobs.
No, but because the log is tight for power of 2 choices, then
That's because it's the online loss. This is an offline thing.
Offline.
Yeah. So you should expect an answer smaller than log m. Because in online thing, you cannot recorrect the poor decisions you had made.
Yeah.
You go like 1 by 1, right? And you put it to the least loaded machine. So that's the online loss.
Yeah.
Yeah.
Thanks.
Okay. Good. So the corollary is price of 2 reservation for identical machines is a constant. And I would like to make a remark here. The stochasticity of the jobs is irrelevant. Like the theorem, we can show it for an oblivious adversary. What this what this means is that, like, as in a corollary of that is that the theorem holds even if the job sizes are arbitrarily correlated. So you still remain within constant factors of the thing you could have done with an M reservation. Okay, so how much more time do I have? 10 minutes is okay. Yeah, and I think I'll be able to. I won't get into too many details for this line of work. Okay.
What about us? Do we get already?
Oh, right. Yeah, please. I'm always happy to talk more about this work. Yeah. So the related work, So Azar et al., Azar, Broder, Carlin, and Upfal, they proved the result for the very special case. And you have M unit size jobs and M identical machines. Okay? It might seem like a very silly setting to be doing load balancing. If you already know there are M unit size jobs and M machines, why not just give each one to one machine, right? But their thought experiment was, if I take each of these unit size jobs and restrict that this job only goes on some two random machines, I place this further restriction, this reservation constraint. What is the optimal make span now? What is the optimal maximum load? They showed that that is still a constant. So it's basically a reservation result, but for this very special setting. And if some of you have looked at cuckoo hashing before, this is due to Pag and Prodler, they do this hashing technique where for each item they hash it to two places and then you try to put the hash value. If it's already full, then that gets evicted, blah, blah, blah.
But this is online.
It's more like, the item, elements keep coming, you hash it to some places, and then if you end up getting stuck in a cycle of these evictions, then you rebuild the hash table and that there's something. I won't get into this, but
This won't be constant because
no, this is still a constant, but it's a different result because there is some sort of adaptivity happening. I'll get into those details a bit later offline, like why, because in online you cannot change your decision. Once you put something somewhere, you commit to it. Here you can still like evict something and then that moves, that might evict something else. But there is some power of two choices happening in this case as well. Okay, now let me maybe give a quick proof sketch of this result. Like how does it proceed? I won't give the full details. By scaling, it suffices to show, just let's say you have deterministic job sizes, P1 through Pn, all between 0 and 1. The total sum is at most M. So the max load is within 1, the average load is within 1. So an M reservation has cost at most 1. What we'll show is that the expected cost of a 2 reservations sigma is an absolute constant, like it's bounded by an absolute constant, as long as sigma has 2 random machines per job. So the proof proceeds in 3 steps. In the first step, what we show is for a fixed sigma, look at one particular sigma, the optimal max load that is achievable in this case, using a max flow min cut argument, you can show that it is roughly the maximum density of jobs. So let me explain what this means. Look at a subset of machines. Look at all the jobs that only have reservations inside the subset of machines R. They have no other choice. They only have to go to machines inside R. So the max load that is induced just on these machines is at least this much. Okay, so this is a lower bound. And max flow min cut and like some very basic rounding ideas, you can show that the optimal max load that's achievable is roughly factor 2 away from this number. And then we can do a union bound over all subsets of machines. This is a bit problematic usually. When you do union bound over like exponentially many things, you better have very strong concentration properties. And that's exactly what we show. That you can just apply like standard like Chernoff bounds for the density of any subset of machines, this expression. And because like each job lands inside a set with probability R over M, because you sample 2 times, not too many things land inside a set R. As in if the set R is small, then the probability that things land inside it is quite small. Even when you scale it down by this, for large sets, also there is like the Yeah, maybe I won't get into the details of this for now. But the idea is that you can use Chernoff bounds on the density and then show that you get very strong decay properties, and the entire calculation goes through, and you get an absolute constant. Okay. So let me also quickly mention our results on related machines. What if you consider related machines? Here, machines have speeds. The load on a machine is the sum of processing time assigned to it, scaled down by its speed. So what are some price of reservation theorems we get? Unlike identical machines, like if you get over there, like 2 reservations had a constant cost relative to an M reservation. Here, log M reservations have a constant cost relative to M reservation. So you never need more than order log M reservations. And price of K reservation for a general N can be as large as the kth root of M over K. Roughly, that's the growth rate. A corollary of 2 is that the price of a little o log M over log M reservation is unbounded. So the right answer is somewhere between log M or log M and log M. What about approximation algorithms? We give efficient algorithms for obtaining, first of all, a true order log M over log M approximation. So if I only cared about K reservations, we can obtain a log M over log M approximate K reservation. Let's say I'm interested in, let's say I'm allowed to have a bi-criteria approximation. Opt has to work with K reservations, whereas alg can use 2 K reservations. Then we show that you can be within constant factors of the optimal K reservation. Basically, like the power of 2 choices thing is happening. Like opt suffers because of its K reservation, but whereas we have like 2 K reservations, so we can manage to stay within constant factors of opt. And then we can also show that there is a 2 reservation whose cost is within constant factors of the adaptive optimum. Imagine an adaptive algorithm which assigns the jobs without knowing their size realization, but after it assigns, it gets the size information. Then it can make the future assignments using this additional information. So a bit more powerful than like just fixing an assignment of jobs to machines. What we show is that 2 reservations can actually match the guarantee of an adaptive optimum when you have related machines. You can't compare against the M reservation, but you can compare against the adaptive optimum. What are some open questions in this line? In this line of work, there's a lot that is still unexplored here, or like we don't have good results. Let me state some more like short-term results. First of all, can we de-randomize this algorithm? Is there a deterministic 2 reservation with cost within order opt M? And how quickly does opt K converge to opt M? Like how large do you have to make it? Maybe like how quickly can you go to within 1 plus epsilon of opt M? Next, for related machines, there are a bunch of questions. I'll just list them here. Maybe I won't talk too much about it in the interest of time. I'm quite fascinated by the setting of restricted machines, so I'll just mention this quickly. In restricted machines, each job can only go on a subset of machines, and that list is given to you. And is there a result similar to the identical machines result? That for each job, you can choose some 2 machines from that list, that restricted list, and still get the guarantees against whatever was the best you could have done with the entire list. Not all the machines. That's not what it is saying. Just the optimal for that restricted instance. And if not, can you still show something against the adaptive optimum? But this is more like a long-term goal. It's quite a challenging problem to think about.
So I have like one.
Yeah.
Okay.
So there's no restriction restricted. There's no restriction on which sets of machines, which lists are given.
The data just is given to you.
Yeah,
This job can
part
go
of the
on
input.
this list. Right. Yes, it's part of the input.
But you choose the 2 randomly from that list, or some.
Just doing randomly won't work anymore. You can show that things can go wrong. Yeah.
So when we say that we have K reservation, we are saying that how many machines are we reserving per job, right? But you're not saying that how many jobs are reserved for a given machine.
Yeah, that usually depends on, like, if there are too many small jobs, it doesn't matter that a single machine is handling them.
But like, do we make any attempt to control that? Because ultimately that's what matters. The total size.
The size matters usually.
Yeah, whatever. I mean,
Yeah.
but the size we're not controlling, right?
It is indirectly being controlled by the random tool, like it is spreading out the load somehow.
So like, are you proving the result for that that a total load with the result of the machine will be only so much?
Yeah, that's exactly the main result, right? It says with a 2 reservation, you can amortize the load within constant factors of the average load.
But that's after the stage 2, right?
Yes, but for every realization in stage 2, this random 2 reservation can actually amortize the load within constant factors.
No, but I guess I'm asking that if you think in terms of the attorney client model,
Yeah.
I'm asking that how much effort does the attorney need to prepare for all the clients in his reservation?
Oh, no, yeah, that is not something that we consider. Correct. That's a fair point.
So isn't that anything that we should be?
It's a natural extension. Yes, exactly. No, he's asking the right questions. If he's running a law firm, he'll want to make sure that one of his attorneys are not unhappy that they have to read up on 100 different cases. Yes, that's a valid question. Yes. Yeah. In fact, that's a really good question. That is, when we talk about context, it also makes sense to say how many different contexts are they learning. Yes, good point. Okay. Yeah. Let me just quickly mention some courses at TIFR that I'm willing to teach. These are like, I looked at the recent offerings. I made a list. Some new courses that I can offer around like advanced algorithms. We can talk about online algorithms, randomized algorithms, optimization under uncertainty, and adaptive algorithms. I've worked on these problems, so I can offer a graduate level course in this. And I can also offer a topics course on stochastic combinatorial optimization, where I cover stochastic versions of knapsack, matching, scheduling, load balancing, many other combo problems. I'm also happy to supervise graduate students here. Concretely, I do have a supervision plan for the next semester at ETH. I'll be advising a master's student on adaptive policies for both symmetric and asymmetric TSP, traveling salesperson problem, and the independent activations model. Yeah. With this, I'll conclude my talk.
Any more questions? Okay, if not, it's shall using 2 to 8, so if you want more evidence.
Sorry, I got confused.
Oh, no, like, I think the model is a bit unusual, so there's always like